Hello and welcome to this APL Quest. See APL Wiki for details. Today's quest is the 10th and last problem from the 2014 round of the APL problem solving competition. We're given a vector of numbers, supposedly non-zero, and we are to say what the largest percentage increase is from one number to the next number. So let's start with a simple test case from the problem statement. And one way that we can do this is by seeing what are the deltas, what are the differences from month to month. So what we want to do is a pairwise difference over this vector. And here it's all constant, but it doesn't matter. And then we want to see this increase. What percentage is it of the month that we started with? So that means the first 20 is an increase over the 80. The second 20 is an increase over the 100. And the third increase is over the 120. That is, there's no increase on the 140, and we can therefore drop the last element. And now we just need to find out what the fraction is of these. So we can write the first part. So that's the increase divided by the month that the month that we started with, its value. And then we get, well, fractions, but we want percentages. We also need to have the largest percentage. So a good idea is to start off by reducing the number of numbers we're dealing with. So we want the maximum percentage. And then we want to convert it into a percentage there. So we need to multiply by 100. Let's make this into a function that takes an argument right there. Here's an interesting thing to look at. This -1 drop. Another way we can think of it is that for every window of size 2, much like what we did to get the deltas, the differences, we want to select the left one. And we can actually write this as a pairwise reduction as well, but instead of a normal arithmetic function, we just want the left value. And if we use a negative number as the window size, just like we did for the subtraction, then we will reverse it. So now left, so this reverses the range. So instead of getting 80, 100, we get 100 and then 80, and then we select the left one. But now if we want to get the right value, which is the first one, then we need to do the right side instead. And what's interesting here is that if we take this definition of A and replace this -1 drop omega, we can with this equivalent sub-expression here, then especially if we parenthesize it, we can see a pattern. So let's start by calling this one, renaming the A here. But we could actually combine these because we are doing a subtraction divided by the right side. That means we can fuse these together to a single n-wise, or in this case -2-wise reduction, and this parenthesis becomes unnecessary. And that looks really neat. That doesn't mean it's a good idea to do it. Why is that? Because certain combinations that are very frequently occurring, for example, a n-wise or especially 2-wise pairwise subtraction, and also the right and the left, those are cases that are special case in the interpreter and optimized, and will run much faster. If we replace them with our fork like this, a 3 train, then the special case doesn't run, and we're going to get significantly worse performance. We can illustrate this just even with a not very large argument. So here's 1,000 random numbers up to 1,000, and let's copy in CMPX from the defense workspace. And then we run the first version, which uses the two different n-wise reductions, and the second version, which uses the fused n-wise reduction, but otherwise are entirely identical. And we can see that yeah, that's pretty hopeless in comparison. So we definitely want to stay with A there. But we're actually not done. We can actually do something more. Let's look at A again, and then let's actually we can start off with B even. Let's start off with B, and then we can do some well mathematics, deriving a different expression for this. Let's start off by taking this train and making it into maybe a slightly easier to read defen. So let's put in our test case here, so make sure it still works. And then we are replacing this train with the defen. So what we need to do here is we have the subtraction of the left argument and the right argument, and then divided by the right argument. Okay, so far we've just replaced the train with a defen. And now, since this is a fraction, right, we have a numerator and a denominator here, that means that we can multiply or divide above and below the division, and the result will stay the same. So let's divide by the right argument here, and divide by the right argument over here as well. Same result, of course, just it's a good idea to check that. And we can immediately see omega divided by omega, that should give us 1. Remember, we said there are no zeros here. At least presumably there aren't. And then this is a difference, and they're divided. So we can split this up into two fractions instead. So we can say alpha divided by omega minus omega divided by omega. And then, of course, this becomes a 1 as well. And we have also divided by 1 here, so that we can eliminate that as well. Okay. Getting there. Now, we're doing a bunch of divisions here. Pairwise divisions. And from every division, we are subtracting 1 from the result. That means we could just break out, we can do all the divisions first, and then subtract 1 from all the results instead. So if we take this -1 and move it over here, so we add -1 to that, get rid of this parenthesis, of course, and then we have a little defen that is nothing but a cover function for a normal division. So we can just put in a normal division there instead. And now we're subtracting 1 from all the results, and then we are taking the maximum of that. That means they would already, the one that's the maximum would already have been the maximum before we subtracted 1. So we can move this maximum before that. The difference here is that instead of subtracting 1 from a bunch of different numbers, we're just subtracting 1 from a single number, namely the maximum one. And here we have a whole new formulation of it that is not only shorter than the original, but actually better performance as well. Let's try it. So we found that A was the fast one, but we derived C from B, where we had the fused n-wise reduction. So C. So why is it that we're having such a significant difference between these two? Well, remember, we're doing the n-wise reductions. Those are the ones that are actually doing a lot of work. And in the beginning, we had two n-wise reductions. We had the one to compute the differences, and the one to compute the origin value that we are to compare the difference against. Whereas in this one, we the work that's being done here is only a single n-wise reduction. So over there we had n subtractions, and then n selections, and then n minus 1 divisions. And here we have just n minus well, it wasn't even n, it was actually n minus 1 subtractions, it was n minus 1 selections, and then it was n minus 1 divisions. And here it's just an n minus 1 division. And then we're doing the maximum, which we have to do anyway. And then we're doing a single -1 plus and a single 100 plus. That doesn't really make a difference there. So that's why that we're cutting significantly down on the time it takes to compute this and the resources it takes to compute this. Thank you for watching.